Hello everyone. In this lecture, we'll be studying about the DC response of CMOS inverter. Now, let us look at the CMOS inverter. We can see this. We have already seen this is a circuit of a CMOS inverter consisting of one PMOS and one NMOS. And the response of CMOS inverter is if V in is equal to 0, V output becomes 1. If V in is equal to 1, V output becomes 0. That is, it inverts whatever is provided in the V in. So, in our previous discussion, we have also learned that if V in is equal to 0, it switches the PMOS on and it switches the NMOS off. As a result, the VDD is mapped to the output. And again, when V in is equal to 1, it switches the NMOS on and it switches the PMOS off. As a result, the ground is mapped to the output. Now, when we go into a DC analysis of it, we have to remember that our KCL, KVL, all these rules of circuits are still valid for CMOS inverters as well. So from KCL we get IDSN is equal to modulus of IDSP. Why we have taken modulus? Because IDSN it's going outward, IDSP it's also going outward from the node. And if we are to consider they're equal, one of the current must come inwards and other must come outwards. Now here the current generally comes from VDD to ground in this direction, which is the opposite direction of IDSP. That is, it's the direction of ISD from source to drain. As a result, we are writing it modulus of IDSP to get positive current and equate the two of them. Now we can solve this equation, but we know that the current of NMOS and PMOS are dependent on a lot of factors. For example, width, the length of the channel, mobility, and the VDD and all. So solving them is a really tedious and difficult task, but we can approach a graphical solution which will give us more insight, and it will give us it will be easier for us to actually understand what's happening in the circuit. Now, before we move on to a graphical solution, let us remember the transistor operation. Here is an IV characteristics. So we will observe for the change in V input and V output, what are the regions of operations of NMOS and PMOS? Are they in cutoff, linear? When they are in cutoff, in linear or in saturation, we'll be learning about those. Let us take a brief recap. In this region where the current has been saturated, here too, these are saturation region. In this region where current is linearly rising with increase in voltage, it is called linear region. And in these regions, it is called cutoff region when no current flows. One thing is to be noted that the curve for a PMOS here is completely opposite than the curve for NMOS. It is because here in this direction we have plotted VDS. For NMOS, for PMOS, VDS is negative, so it's going that side, and current is also negative as we have plotted minus IDSP. Now, if we want the current to, if we take the modulus of the current, we will get here, and if instead of VDS we plot VSD, the curve will be shifted rightwards. Now, let us observe the NMOS operation. For cutoff region, we know for cutoff, the gate to source voltage of NMOS has to be less than threshold voltage. We have known that in linear region, in linear region, inversion region has to be created. Since inversion region has to be created, the gate to source voltage must be greater than the threshold voltage. And again, drain to source voltage must be lesser than the gate to source voltage minus VTN, so that it doesn't pinch off. In saturated region, the gate to source voltage again has to be greater than threshold voltage to create the inversion region, but the drain to source voltage must be greater than gate to source voltage minus threshold voltage, so that there is a pinch off created. Now in this circuit, if we observe, our output is actually the drain to source voltage, and our input is actually gate to source voltage. So we can write VGSN is equal to V in, VDSN is equal to V out. If we write that, we can say that V in, for cutoff region, V in has to be less than V threshold. For linear region, V in has to be greater than V threshold, but V out has to be less than V in minus V threshold. And for saturation region, again V in must be greater than V threshold and V output must be greater than V input minus V threshold. These three conditions we'll have to remember when we try to solve the actual equations. For NMOS, the case is almost same. The gate to source voltage must be greater than the threshold voltage. It is to be remembered that the greater threshold voltage here is negative. Again, gate to source voltage, this is for cutoff region. For linear region, gate to source voltage has to be lower than threshold voltage, and the drain to source voltage has to be greater than VGSP minus VTP. We can see the conditions are exactly opposite as in case of NMOS. In the circuit, we can see here V in is equal to gate to source voltage, this voltage, plus VDD plus this voltage. So we get V in is V in minus VDD is equal to VGSP. This P indicates PMOS simply. And again, drain to source voltage, that is this is the drain, this is the source. So drain to source voltage will be equal to the output voltage, this voltage, minus the VDD, we'll get this voltage. So VDSP is equal to Vout minus VDD, VGSP is equal to V in minus VDD. From there we get VGSP in case of cutoff has to be greater than VDD plus threshold voltage. Again, V in has to be greater than VDD plus threshold voltage. Again, V in case of linear region has to be lesser than VDD plus VTP threshold voltage. And again, VDSP or V out has to be greater than VDD plus V in minus VDD. We are replacing VGSP minus VTP. So this positive and negative VDD get cancelled out. So V output has to be V in minus VTP. Again, in this case, V in is lesser than VDD plus VTP, and in saturation, V out is lesser than VDD plus V in minus VDD. This whole thing is VGSP minus VTP threshold voltage. So this positive and negative VDD are cancelled out. So here V out has to be greater than V in minus VTP. These three conditions will again have to be remembered when we look into the operation of a CMOS inverter. Now let us observe the IV characteristics of NMOS and PMOS together. This is the IV characteristics of NMOS, and this over here is the IV characteristics of PMOS. Now, if we one thing is to be noted that we have taken modulus of current, which makes the IV characteristics the current value of PMOS positive, and for the NMOS we have plotted VDS here, which is equal to the input V in. For the PMOS also we have plotted V input, which is equal to VDS plus VDD. Because of this, the voltage point has shifted by VDD towards right. Now, for load line analysis or graphical analysis, we will be taking a V in for a particular value of V in. We will be calculating V out and currents. One thing is to be noted that V out must be where the currents are all equal, because we have to satisfy KCL. So at every point we will be considering the places where the currents are equal. Now let us look at the load line analysis. When V in is equal to 0, we see that when V in is equal to 0, our NMOS will be in cutoff region while our PMOS will be completely on. As a result, the NMOS curve and the PMOS curve will meet here and meet here. As a result, the output voltage is equal to VDD. If we increase V into 0.2 volts, we can see that the level of current in the PMOS decreases. Why does that happen? That happens because if V in increases, V in minus VDD eventually decreases. V in minus VDD eventually decreases. As a result, VGSP decreases. Decrease in VGSP eventually decreases the current, and because of this current, and again in the similar way, since when Vin increases, VGSN gradually increases, and when VGSN increases up to a certain level, when it becomes equal to or greater than threshold, it starts allowing current to flow through it, and as a result we will get very low amount of current in NMOS here and very high amount of current in PMOS, and the output voltage will be a little less than VDD, but it will be very high again. Now if we increase the Vin any further, what would happen? We have seen that the voltage level of the current level of PMOS has further decreased due to decrease in VGSP, and the current level of NMOS has increased. As a result, they meet here. At this point, the current in the NMOS and PMOS are equal. As a result, Vout further decreases. When we change Vin to 0.6 volts, we see that the current in NMOS has risen by a great amount, and the current in PMOS has fallen down by a great amount, and we get the output here. Everything over here we see is related to this, because if we increase the Vin, what happens? VGSN increases, which increases the NMOS current, and VGSP decreases, which decreases the current of PMOS. And we get the output, which is very close to 0, but not 0 at this moment. Now if we increase Vin up to 0.8 VDD, again we see very low amount of current passes through PMOS and a high current passes through NMOS, and we get a value of voltage output which is very close to 0. If we further increase VDD, if Vin is equal to VDD, the NMOS comes at cutoff, the PMOS is at cutoff, and the NMOS has a very high value of current, and we get V output is equal to 0. One thing is to be noted: for comparative result, the beta of PMOS has to be equal to beta of NMOS. If they are not equal, what happens we'll be seeing in this lecture at a later time. Now if we plot the relations, we see when the we have plotted Vin in x direction and V out in y direction. When the Vin was very little, equal to 0, V out was is equal to VDD. As the Vin increased little by little, the V output started decreasing. Let us say this is for 0.4 volts of Vin, and this was for 0.6 volts. When suddenly there was a transition, and after that point, if we started increasing the Vin, the V out gradually decreases, and V out gradually decreases to 0 when Vin was equal to VDD. We think from the previous example we have seen that the transition occurs between 0.4 volts to 0.6 volts. So here is a huge slope from 0.6 to 0.4 to 0.6 volts. This graph over here is called the transfer characteristics of a CMOS inverter. Now transfer characteristics, we can divide the regions into 4 parts, A, B, C, D, in 5 parts, A, B, C, D and E. So in part A, here we know when the VDD, when V out was almost equal to VDD, or Vin is almost equal to 0, our NMOS was off and our PMOS was completely on. So NMOS was in cutoff region and PMOS was in linear region. Gradually, when we increased the value of Vin, the output voltage gradually decreased. At the level B, we have seen that the NMOS is in saturation region, PMOS still remains in linear region. When we further increase at one point of time C, where we see a sharp transition, we see our NMOS and PMOS both are in saturation region. Then after further increase, say Vin is equal to 0.6 volts, we see that the PMOS was almost off and NMOS was completely in linear region. So PMOS was in saturation region, NMOS was in linear region. On further increase of Vin, we have observed that the NMOS remains in the linear region, but the PMOS is completely shut down and is in the cutoff region. Now that curve is true if beta P and beta N are equal. That is, if beta P and beta N are equal, then the transition or the sharp transition occurs at VDD by 2. If they are not equal, then the sharp transition switches from VDD by 2 either to the left or to the right. If beta p by beta n increases, for example, it increases from 0.5 to from 1 to 2, 3, 4 up to 10, we can see that the sharp transition or the transition between the on and off states becomes closer to VDD. It moves towards the right and becomes closer to VDD. Again, when beta p by beta n gradually decreases, we can see that the transition moves towards the left and the sharp transition region, that is the switching point of the MOSFET, moves close to ground. So we can safely say that if the mobility or the width of the PMOS is very high, then what happens, we get switching at a voltage very close to VDD. If the mobility or the width of PMOS is very low as compared to NMOS, we get switching close to our ground, or we get switching close to zero voltage. This type of behavior is called skewed gate. Noise margin is an important factor when we are considering any CMOS circuit. Now, noise margin is how much noise can a gate input see before it does not recognize the input. For example, in this circuit, there are two inverters back to back. That is, if the input is 1, the output will be 1. If the input is 0, the output will be 0. So, the noise margin will say, if this input value, we are considering input as 1s and 0s, but actually 1s are VDD and 0s are ground. So, it says that whatever the input is, the input might not be equal to VDD, input may change, input may have fluctuations. For example, let us say VDD is 5 volts, but the input might be 4.5 volts, 4.3 volts. Will the circuit consider 4.3 volts as logical 1 and give output as 1? Or will the circuit consider 4.3 volts as logical 0 and give output as 0? Or it will give a floating output? We don't know. And in order to know that, in order to understand that, we have to understand noise margin. Now, we see that this is the maximum level of high output, logical high input that we can allow, and this is the maximum level of logical low input that we may allow. Again, this is the level of maximum logical high output range, and this is maximum level of logical low output range. Now, we can shift these values upwards or downwards by changing our designs. Again, we can shift this value upwards and downwards, but input noise level is unpredictable. We want some of this intermediate region because we want a gray area where the input is neither 0 nor 1. Because of noise, if we get 2.6 volts, we cannot say this is either high or low. So we need an intermediate region. Let us suppose this can be from 5 volts to 4 volts, and this can be from 0 volts to 1 volts. This is just two examples. Now, noise margin is the difference between the maximum. If there are two types of noise margin, one for high, another for low end. So, for the low end, the noise margin is the difference between the maximum level of the output that we consider as low and the maximum level of input that the gate recognizes as low. That is, for example, if we suppose this is 1 volts and if we suppose this is 0.5 volts, we can say that if it sees an input of 1 volts, it will give an output of 0.5 volts, and it will consider 1 volt as low, and the output of 0.5 volt will be considered low. If the output is 1 volt, we will not consider it as low output. Again, if the input is 1.5 volts, we will not consider it as low input. It will reach the intermediate region. So this difference over here is called the low end noise margin. In the higher end, we will see the minimum level of logic high output range and the minimum level of logic high input range. Their difference will be the noise margin at the higher end. Now, we want this noise margin to be maximum. Why do we want it the maximum? Firstly, we want logical high output range to be small. Why do you want that? We don't want to design any gate which gives an output of 4.2 volts. Suppose we want a gate which will either give output of 5 volts or give output of 0 volts. If not 5 volts, it can be 4.9 volts. If not 0 volts, it can be 0.1 volts. We do not want these values to fall too much. So we want this range to be as low as possible, and we want this range to be high, but not so high that the intermediate region is so low that we cannot differentiate whether an input signal, a noisy input signal, is high or low. As a result, we have to design in such a way that this lower and higher noise margin are high and maximum, not so high that the circuit does not operate properly, and not so low that it is intolerable towards the noise provided at the input. And that is done by using unity gain points. So this is the curve for beta p by beta n is equal to 1, and these are the unity gain slopes, that is -1 gain here and here, where the points where we get unity gain, we are considering this as high noise level of the output, and we are considering this as low noise level of the output. If we take these 2 points as the high and low noise levels, we will get maximum noise margin. In this noise margin, the circuit will perform as required, and it will tolerate the maximum level of noise in the input. That's all for this lecture. In the next lecture, we will be learning about transient characteristics. Thank you.